Hello and welcome. So today we're going to be talking about chords with circles. So remember, a chord is essentially a line segment in a circle where both endpoints are on that circle. So C to D is an example of a chord in a circle. You can also say that E to F is a chord because both F and E are endpoints on the circle, right? Or on the circumference specifically. All right. So there's a couple properties we can talk about with chords and circles. The first major one is going to deal with the angles and arcs with chords. All right, so this is when you have two chords that are intersecting with each other. Now, the property is, I'm going to give you like the general one and then kind of give you the more mathematical notation thing, is the angle in line with given arc. So when we say like, let's say that we're given the arc of E to D, and that we're also given the arc from C, B to F, right? That whole arc there. The angle in line is going to be one of those two yellow angles because those are vertical angles. We know they're equivalent, right? So either of those two is the angle that's when we say in line with given arcs, is that if you were to draw a line between those three arcs, which angle would it have to be? Now, it's clearly not going to be this angle here because you'd have to cross line segments to get there. It's what angle do you actually have that's running through the vertex, but not any of the line segments of the chords, kind of a thing. All right. And so it's going to be angle in line equals 1/2 of your major arc. Major here is just going to be talking about the arc that is larger than the other, right? So ED is considered the minor arc in this case, even if it was larger than 180, because it is smaller than the other arc, right? So we're going to be talking major versus minor as a comparison of larger versus smaller arcs there. So mathematical notation, angle CGF is going to be 1/2 of measure of arc FBC plus the measure of arc ED. All right, so if the general property doesn't really float your boat, there you go. So let's actually practice this. Let's set up some equations, work through it. So first off, example 1, it says find the angle or arc for each of the following. So X is our goal, right? That is our angle we're trying to find. We're given two arcs, this arc of 119 and this arc of 171. So the angle in line, if we were to draw an angle through the vertex of that intersection of the two chords, right, you'll notice it hits the 171 and 119. The angle in line is X, the angle we need. So the angle in line with arcs equals 1/2 the major, and the larger of those two is the 171, plus the minor, 119. There we go. That's the setup, right? You'll notice the thing we need to find is already solved for, right? It's alone, so simplify the right side and we're done. So 1/2, 171 plus 119 gives us 290 degrees, right? So then from there, half of 290 is going to give us 145. Yeah. Right? And that is the measure of X, the angle. There we go. Let's do another. Same thing, we're given this arc and this arc. So that means the angle in line would be these two, but that's not what we're trying to find, right? Our goal right here is X. So how does X relate to the angles that are in line? Well, keep in mind you have a straight line right here, and all angles along a straight line add up to 180 degrees. Now keep in mind that this arc is not 180 degrees because we don't know if this is the diameter or not, but we do know at least that these angles will add up to 180. All right, so let's actually find it. So we know that X isn't the one in line, so I'm going to call that W for now, because why not? So I'm going to say, okay, so angle in line, so W equals 1/2 the major, that is 154, it's larger, plus 146, the minor. And keep in mind, the order actually doesn't matter here, simply because it's addition, right? 146 plus 154 is the same thing as 154 plus 146. Something to keep in mind. So when we add those two together, we get 300. So 1/2 of 300 equals 150. So that means that W, right, is 150 degrees right here. And if I know this whole thing is 180, that means that X must equal 180 minus 150, or in other words, 30 degrees. So X equals 30 degrees. Oops, kind of dropped my degree symbol on a few of those. There we go. And there's your answer for that one. Not too shabby, right? Just keep an eye on what you have. So this next one we have arc, which means the angle in line, right, run through the intersection point would be our 7x plus 17, huzzah. So we say, great, the angle in line with the arcs equals 1/2. Now this one diagram tells us the major would be 4x plus 14. Common sense tells us that 6x plus 15 is technically larger. Again, for the same reason, right? Major and minor does not matter as far as addition goes, right? Order, it's not a big deal. I'm just going to follow the diagram. Diagram shows us relationships. So I'm going to say the major is 4x plus 14, and we're just going to say the diagram is not to scale on that one. Plus our minor, 6x plus 15. And then we just simplify. So 7x plus 17 equals 1/2. Combine like terms, combine your x's. So we have 10x plus, combine numbers, 29. Now between you and me, I don't like taking half of odd numbers. That's kind of a pain. So I'm going to multiply both sides by 2. So that simplifies to 1. So we have 1 times that parenthesis 10x plus 29 equals, and then 2 parentheses 7x plus 17. Now, I just wrote this out on the right side to show that that 2, when we multiply, it technically multiplies to everything because the 1/2 is multiplied to everything. So when those simplify, what's happening is that you're distributing 1 through. Sometimes I have students who like to double this, double and double. They times everything by 2. That's actually multiplying by 4, because multiplying 2 on the outside is the same as multiplying that inside as well. So do keep that in mind. Distribute the 1, we get 10x plus 29. It's not going to change. On the left side, distribute that, we get 14x plus 34. And then we just finish simplifying. So I'd say, okay, well, let's subtract 10x. All right, I like the x as positive. That's why I'm subtracting 10, because why not? I'm going to move the 34 over while I'm at it as well. So then we end up with 4x equals, and then 29 minus 34 is negative 5. Divide 4, divide 4. So x is negative 5/4. Now you may be looking at that and you're like, ooh, negative number, does that work? Well, double check it, right? Before, our answers didn't have to really be checked because we got positive numbers. Yeah, 145 and 30 would make sense in the diagram, right? But here, negative 5/4, be careful, right? When we're looking at geometric diagrams, lengths can't be negative, right? In a diagram, that angle cannot be negative either. Negative angles are fine if it's not restricted in diagrams. This is, because it's in a diagram. So I say, okay, let's plug it in. So we have here 4 times our x, which is negative 5/4, plus 14. That gives us 9. 9 is a positive number, which means we have a positive length there. Positive lengths are fantastic. We love them. It's not an issue, right? The next one, we have 7 times negative 5/4 plus 17, positive number, that's good to go. 6 times negative 5/4 plus 15, I believe the number was, positive number. Right, they're all positive, which means that this valid answer, x equals negative 5/4, you're done. Okay, so that's the first property with angles and arcs with chords. The next one is talking about the lengths of those chords themselves. So your general property is as follows. The small length, so pick a chord. So I'm going to pick that one right there. So the small length of the chord times the remaining larger length. Okay, so the product of the two lengths in a single chord is equal to the small length of the other chord times its larger length. So in other words, if you have two intersecting chords, right? Intersection point there. That's going to cut your chords into one smaller or one longer length. And again, because it's multiplication, you can do large times small. You can go the other way. 2 times 3 is the same thing as 3 times 2, right? It's saying that the product of the two lengths of one chord is equal to the product of the two lengths in the other chord. That's all this is saying. So mathematically, if you wanted to write that out notation-wise, D to G times G to C is equal to F to G, times G to E. Okay, so small length times large equals small times large. So looking at this other one, essentially, we're going to say smaller length times larger length. So 8 times X equals the smaller length times larger length, 6 times 12. That's all this property is. That's it. The products are equal to each other. So 8x equals 72, divide 8. X equals 9, right? X is representing a length, so it's a positive number. That works. Yay. Okay, that's it. That's as crazy as the property gets. So same thing with this one. We'd say, okay, smaller length times larger length, so 12x, which I think diagram 12 might be a little smaller, but that's okay because multiplication is commutative. It goes both ways. Equals small times large, so 3 times 2x plus 7. I put parentheses because you need them. You're multiplying the smaller to all of the larger length, not just part of it. You need parentheses to notate that. 12x equals 6x plus 21. Right, keep solving for x. I'm going to get a lone. So 6x equals 21. Divide 6. And we get 21/6 as an answer. That does simplify, right? 3 is a common number, so 7 halves. Now keep in mind, double check your answer. As I put this in, a positive times a positive number plus 7. That is for sure a positive number. I don't need to know what it is to know that it's positive. We're good to go, right? Multiply two positives, you get a positive. Add something to a positive number, you're getting a positive number, right? Or I should be more specific. You add a positive number to a positive, it'll be positive. All right, there you go. Example 3, still not even too bad. The solving is probably the most crazy part of this thing. So small length times large length of one chord equals, swip to the other, small length times large length of the other chord. And then we just solve. So solving for x isn't going to be helpful with those parentheses there. They're not set to 0, they're set to another expression. So multiply it out. 30x squared plus, and then 19 times 5, 95, I believe, 95x equals, and then other direction, we would have 10 times 3x, so 30x plus 140, right? Hold on. 5 times 19. Yeah, it's 95. I kind of doubted myself there for a minute. Okay, now we just need to finish solving. So when we're looking at that, I'd say, okay, first thing I see is an x squared. And those are hopefully ringing bells that you need to use one of your quadratic solving methods, whether that's completing the square, factoring, or the quadratic formula. Pick one that you know and go with it. I like factoring, which means chuck everything onto the same side. So I'm going to subtract all of these over, right? So on the right, those cancel, give you 0. On the left, we have 30x squared plus 65x minus 140. And there we go. Now we just need to solve this. Now, I like factoring. Factoring first step, take a GCF, right? 5 is your common factor here, so then you would be left with 6x squared plus 13x minus 28 equals 0. Now I factor using big X methods. Whatever method works for you, go for it. Add to your middle number, multiply your first and last. 6 times negative 28 gives us negative 168. 21 and negative 8 are the two numbers that do that. 21 minus 8 is 13. 21 times negative 8 is negative 168. There we go. Huzzah! Right? Now keep in mind that your leading coefficient is a 6, which means divide by that number and simplify. Right? That is going to be the same thing as 7 halves. This will be negative 4 thirds. So GCF, first parenthesis, it's called the bottoms up method because the bottom comes up is x's coefficient. Same thing, 3x minus 4 equals 0. So factored, yay! And if factoring is not your cup of tea, quadratic formula or complete the square. All right, and then you set your factors to 0, so 2x plus 7 equals 0, 3x minus 4 equals 0. Notice I didn't set 5 to 0 because if I tried to, is there any x for you to solve for? No, right? That doesn't give you any solutions. 5 equals 0 is not true, so there we go. And then we just solve. So minus 7, divide 2, right? So those cancel, x equals negative 7 halves. Add 4, divide 3, so x equals 4 thirds. And check your answers, right? No negative lengths or lengths of 0. And I can already tell you which one's going to fail. Because if I plug that into my 5x, 5 times negative, right? Positive 5 times negative 7 halves is a negative number. And you can't have a negative length, which means that that's going to kick the bucket. You cannot use it. Now, 4 thirds will work. That one's not going to have an issue. Because a positive times a positive, that works. Positive times a positive, adding a positive number, yeah, that works in both of those. So 4 thirds is a good solution to use. Okay, there's your second property. Last but not least, one more, chords with a radius and a circle. Okay, as our last property, we're so close. All right, so first off, this is a particular situation when you have this is the center, by the way, center of your circle. And if you were to draw the G to J, continuing on, that is a radius of a circle, that's when this property really hits home. Okay? You're essentially being told that J, let me not go over it, is a midpoint, meaning that it cuts I to J and J to H into 2 equal segments. All right? They are congruent to each other. And then it also follows that if you have that, then you have that J to G, that segment, is perpendicular to IH. Or in other words, you have a right angle here and right here as well. Okay, so essentially what happens is that if you have a radius and a chord that intersect at a right angle, or if you're told that J is a midpoint, right, if you have any of those, one of the 3 things, you are guaranteed the other 2. That's kind of what this property is saying. Just having a chord and a radius isn't enough, right? Because if I have like a chord here, I mean, you can always find a radius that will hit at a nice 90-degree angle. But if I draw like my radius right there, it's not a right angle. So it's always a specific, it has to hit at one point, but it will always exist that you do have one for pretty much most chords out there. So do keep it in mind, 'tis a thing. All right, but if you have one of the 3, you're guaranteed all 3. So let's practice, shall we? So example 3, it says solve for indicated variable or length. So we're told that B to M, that whole thing, is 8. We're told that B to E, that whole thing, is 11.2. And then we're solving for x, which is this length right there. Now we are given in our diagram a right angle, which then gives us all of the properties that we talked about right there, meaning that this point where it meets is a midpoint of the entire segment, meaning that those 2, B to the midpoint, let's just call that M's already in use, W. B to W and W to M, those are congruent segments. So if the whole thing is 8, that means it splits evenly in half, via midpoint. That means that this, let me use a different color now, B to W is 4 and W to M is 4, splits that nicely. And you can also do the same thing with B to E. Notice that this is the center of your circle, right? Because it's heading at that 90 degrees. Once you have one, you have all, right? Which makes this a diameter of your circle, which means if I were to look at just that inner portion right there, that's 5.6, right? Because we know half of the diameter is the radius. And you say, oh, well, this is so nice, as it should be, because you'll notice that right now you are staring at a right triangle. And what magic theorem do you have for right triangles to find lengths? Why, the Pythagorean theorem. Remember, the Pythagorean theorem is leg squared plus leg squared equals the hypotenuse squared, and you just happen to have 2 out of the 3 lengths. One of your legs is 4. The other leg is what we're trying to find, equals our hypotenuse squared. Voila. Right? There you go. That literally is it right there. So I'm going to plug this all into my calculator at once. So I'm going to subtract 4 squared. Yes, I know that's 16. I'm just too lazy to write it. So x squared equals my 5.6 squared minus 4 squared. I say, okay, well, I undo squares with square roots. Now, technically, again, plus minus is a thing, but x is a length, and you can't have negative length, so you don't need to worry about plus minus. So x equals whatever that number is. So I'm going to go into my calculator, and I'm going to say, great, the square root of 5.6 minus 5.6 squared. There we go, minus 4 squared. Now, if it wanted the exact answer, this wouldn't quite work. You would have to do it separately, so 5.6 squared minus 4 squared, right? And then take the square root of that fraction, which isn't too bad. And then that would simplify it. That would be your exact answer. But if it wants the decimal approximate, which is what we're going to do here, then you're totally fine to go with that top number. So 3.919. So x equals 3.919. Fantastic answer to use. And there you go. That's it. Okay. Now, sometimes I have students who ask me the question like, oh, Miss Diddy, well, isn't that just 5.6 minus 4? So in other words, 1.6. You'll notice we're 2 very different numbers, is that sometimes students like to think that the squares and square roots cancel out. Keep in mind that if you have this, 5.6 squared minus 4 squared in a square root, that is not the same thing as having this. Very, very different things. And the main reason why you can't separate it out is that subtraction. Square roots, radicals, those are technically exponents. And if you have an exponent, right, you cannot distribute that exponent over addition subtraction. If that was multiplication right there, absolutely free game. But if it's addition or subtraction, you cannot distribute that power of 2 to each one of those individually. And it's the same thing with square roots. Because of addition subtraction, because of that subtraction, you can't distribute that square root. Do keep it in mind. It's a thing. Just wanted to mention it. Okay, so that's the first problem. The next, we have this one. So we have 3.8 is that distance, x is this distance, and 5.6 is that one. And then we say, okay, well, first off, we have some important info here, and that's that right angle, which tells me that z is now a midpoint, because if I have that right angle, I know this is a midpoint, which tells me that if this is 3.8, well, that should also be 3.8. Huzzah, right? And I say, okay, well, that's some really nice, good information right there. Well, typically you're going to want to use the right triangle, so that's going to be nice. What is that distance right there? Do I know what that distance is? I highlighted it in blue for a reason. Yes, that is blue for a reason, because that is the radius, right? A radius goes from center of the circle to the outside. So does that, which means that's also 5.6. But more than that, wouldn't you agree that A to Y is also a radius, center of a circle to outside? Oh, Yeah, that means that this whole distance is also 5.6. Well, that means that if I can find what this last little leg is right here, right, if I subtract that out of 5.6, that finds the x, right? So x equals the radius minus that last leg in the circle. I don't know, let's call it, I'm going to use W again. W is a great letter. All right, so I'm going to call that W. So that means 5.6 minus that leg of the triangle equals the remaining portion, what you're trying to find. So really just kind of play with what you have, know your properties, and a lot of it kind of falls into place. Okay, so you can Pythagorean theorem this way, right? You could say that leg squared, so W squared, plus the other leg, 3.8 squared, equals our hypotenuse, 5.6 squared. I'm going to subtract that 3.8 squared, all right, and take that square root. So W equals the square root of 5.6 squared minus 3.8 squared. Can't distribute the square. I'm just going to check that whole thing to my calculator, right? Go the bottommost round. So we have square root of 5.6 minus, what was it, 3.8, I believe the number was. Yeah, it was. Okay, so then we have this 4.1133, so on and so forth. That is going to be our number for our W, right? There we go. Let's go back in. All right, so that's going to be what we're looking there. And I'd say, okay, well, I'm just going to take that number, right, and subtract it from 5.6. So I'm going to come back, and I'm not going to round it off yet. I'm going to use that entire decimal. I'm going to say 5.6 minus that whole thing, right? And we get 1.4866. That 6 is going to round up, so 1.487. So x equals 1.487. Right? And I wouldn't bother even like writing it out in a step here. Like I would grab that whole decimal and chuck that into W, right? Rounding off too early can create round off error. I would only round my answer till I actually get my answer, right? Other than that, I would use the whole decimal. So to keep in mind, 'tis a thing. But that's kind of how you would solve that one. All right, see, same process. It's really playing with the information you know. So you know that this is 10. That's 11. We don't know what the radius is, but that's our goal, right? R equals something is our end goal. And we're given one last piece, right angle. And as soon as you see the right angle, you're like, oh, yes. That means Z is a midpoint. And that means that has to be 11 as well. Well, we can play with the radius. I know that that is also a radius length, which means this is also a radius length, which means that in order to find this little extra piece right over here, let me use an orange to make it really obvious. In order to find this, well, isn't that just the radius minus 10? Right? If I know the whole thing is R and this little snippet is 10, R minus 10 has to be the remaining piece. And there you go. Isn't that all three sides of the triangle? Yeah. And that's totally fine to set this up in the Pythagorean theorem, because when we do, so leg squared plus other leg squared equals hypotenuse squared. When we do, you'll notice there's only one variable, and that's the R. And it's totally fine for this, like the more R's in the equation isn't going to hurt it. If you had a second variable in there, that's going to make it a lot harder to solve. I say, okay. Let's distribute these parentheses. So I'm going to go a little quick. So we get R squared minus 10R minus 10R plus 100, right? Plus the 121 plus equals R squared. And then we just finish it off, right? You want to get all of your R's on the same side, but notice as soon as you subtract R squared, what happens to your R squared term? Gone. So we have negative 20R plus 221 equals 0. Solve for R, right? I like positive R, so I'm going to add 20R to the other side. So we get 20r equals 221. So divide 20, and there you go. 221 over 20, isn't that going to simplify? That is as crazy as it gets, which means r equals 221 over 20. And that is the exact answer. If you wanted the approximate, you could literally just say 221 over 20 in a calculator. 11.05 ends up being an exact decimal anyways. So there you go. And that is how you would kind of solve these. So be careful. Just make sure you know what you're looking at, right? As soon as you have that right angle, it really guarantees a lot for you and you can play with it. Just make sure you know what you have and how does it relate to the stuff around you. And usually try for a Pythagorean theorem set up for your equation for anything like this. Anyways, those are some good problems, and that's pretty much everything there is to know about chords inside of the circle. Thank you so much for watching.